Okay, so now we're going to kind of go back to what we were talking about in the previous chapters, where we were talking about acids and bases, and we were doing some stoichiometry with them. Well, here's the funny thing. Some acids are really strong and really dangerous, and some acids not so much, right? They're actually kind of helpful to the body, like, say, vitamin C, which is ascorbic acid, or aspirin, which is acetylsalicylic acid. They're good for the body, some of them, and they're not so dangerous. And so what we're going to talk about here is strengths of acids in this and bases in this particular unit, and we're going to do more with that as well. So water has this funny thing. It's called amphoteric. That means it can act like an acid and a base. And we're going to talk a little bit about pH, not a whole lot. I think that's really primarily in the next unit. The difference between strong acids and strong bases. So water acts like an acid and a base because it has this ability to self-ionize. Most acid-base reactions that you guys are going to deal with are aqueous solutions. And water can act as either an acid or a base depending on what it's mixed with. If it's mixed with an acid, it will act like a base. If it's mixed with a base, it will act like an acid because it's amphoteric. It has the ability to self-ionize. It means two water molecules break apart into an H3O plus and an OH minus. One of the H's gets donated over, and you get this, making this the acid, and this gives it up. Sorry, this is the acid, and this is the base, and it produces H3O plus and OH minus, which is the stuff that makes acids dangerous. It's the more H3O plus or the OH minus. So because this is an equilibrium, we're going to write a KQ. So K, just like any other K, is products, H3O plus, raised to its coefficient, multiplied times the hydroxide, raised to its coefficient. But if you notice, in my equation here, I'm not going to include liquid water. And the reason why is because it's a liquid. So this has got a special K, and it's called KW. It's an equilibrium constant for water, and it's the same always. The KEQ is called KW for water. H3O plus times OH minus is always this value at 25 degrees. So to calculate the amounts that you have of each in pure water, I'm going to set up an ice table. You thought you were done. You are not. So I'm not going to include these guys because they're both liquids. So this starts out as 0. This starts out as 0. They're going to gain X and gain X based on the fact they both have coefficients of 1. So at equilibrium, you've got 1. So I've got KW equals X times X, X squared, equals 1e negative 14. X is therefore 1e negative 7. 1e negative 7, 1e negative 7. Look at that. The amount of acid character and base character are equal in pure water. So I'm going to erase that. Oh, I might have had room for it. Oh, well, it's gone now. Anyhow, in any aqueous solution, the amount of the H3O plus multiplied times the amount of OH minus is equal to this value. If the H3O plus, the acid character, is greater than the base character, it's an acidic solution. If the amount of OH minus, the base character, is greater than the acid character, it's an acidic solution, basic solution. And if you have them equal to each other, as in pure water, it's neutral. That's why water is neutral, because it has equal amounts of acid and base character. That's what makes water neutral. So I'm going to ask you to get out your calculator. Keep in mind that these two always multiply to make 1e negative 14. So if I've got this one and I'm trying to find the hydroxide, I'm going to take 1e negative 14 and I'm going to divide by the number to find the other one. So if I take 1e negative 14 and divide by this, check it on your calculator, make sure you get 1e negative 9. Do the same thing going from here to here. 1e negative 14 divided by the number. Do it on your calculator. Make sure you get 1e negative 11. Alright? Then the next one, I'm going to do 1e negative 14 divided by 2.1 e negative 8. The calculator had something on it. 4.8, E negative 7. And again, make sure your calculator is saying the same thing mine does. .4, E negative 4, 1E negative 14 divided by 4.2, E to the negative 12, 0.0023 or 24, you round up, 1 E negative 14 divided by 8.4, E to the negative 8, 1.2 E to the negative 7, one last one, this will be 1 E negative 15. Okay? So now, determining whether it's acidic or basic, you're going to look at these numbers and you're going to determine which one is larger. Which one's greater. Okay? But you don't want to look at the number in front. What you want to look is you look at the powers. Because remember, this means 0.000001. This is 0.000000, 8. Nope, that's 8, 1. The closer this number is to being 0 or a positive exponent, the bigger the value is. So I'm looking at negative 5 is going to be acidic because this is my acid character. I look at negative 3, closest to 0 or a positive number, base character is greater. Negative 7 versus negative 8, base character, just barely. Not really a very strong base here at all. Negative 4 versus negative 11, acidic. And this one, it's hard to compare because that's not in scientific notation. But if you notice, negative 12, that means there's 11 zeros this direction. It's got to be basic. Okay? And again, this one is very, very close, but this one is technically larger, so it is acidic. It's slightly acidic, but it is acidic. And then here, definitely much larger, because that is 1e to the first. The bigger this is, closer to 0 or a positive number, the stronger that particular characteristic is, acid.